In this video, we're going to continue our discussion on integration and learn how to use integrals to calculate the volume of some three-dimensional objects. We're going to start with a method of slicing using discs or washers, and in the next video, we'll learn a different method for finding the volume of these three-dimensional objects. Now, either method works just the same. It's just sometimes one of the methods is going to be way harder than the other. It all depends on the situation that you have. So let's just start with learning this first method. I think this one usually is a little more intuitive for students, which is why it's a good one to start with. But sometimes the other method ends up being easier. It really all just depends on your problem. So the basic idea of what we're going to do is think about finding the volume of different objects. You've done volume before in geometry classes. You know how to find the volume of a cylinder, for instance. We have a formula for that. But what if we had to find the volume of a really strange, irregular object, not a nice geometric shape? What if we had just some three-dimensional blob type thing and we want to find the volume of it? Well, we learned with our definite integrals that we could figure out the area of really weird shapes by cutting the shape into strips and estimating the strips with rectangles, adding all the rectangles up, and taking a limit. We're going to use a similar idea here, except we're going to split the volume into cylinders, add up the volumes of all these cylinders, and take a limit. But it's a very similar idea, it's just one dimension higher. So I have an idea of chopping our weird objects into cylinders. So let me just outline for us the theory of what we're going to do, and then there's going to be a lot of examples so that we get the hang of it. So our idea is we are going to intersect a solid that I'm going to call S with a plane to get a cross section. And then we're going to let A of X be the area of the cross section in a plane perpendicular to the x-axis. And right about now, I can already hear you on the other end saying, what in the world are you talking about? And that's because this explanation here is a little bit jargony, and I'll fully admit that. But what we're doing here is we're imagining, let me just draw some random object here. Here's my X and Y, here's my blobby three-dimensional object. So imagine that thing is three-dimensional. When we're saying we're taking a cross-section by intersecting it with a plane, and then we're looking at the cross-section of the plane perpendicular to the x-axis, that's a really fancy way of saying, imagine taking a knife and slicing this like a loaf of bread. We're going to be slicing this blobby homemade loaf of bread, and then finding this area of what would happen when I take a slice and open it up. So if you imagine that we've sliced up a loaf of bread like that, and then we're turning the slice that we just took and finding the area of this part of the bread. So the area of the cross-sectional face is what we're talking about. A of X is taking our slice, opening it up, and looking at that surface and finding that area. So just imagine slicing up a loaf of bread, finding the area of the face of the bread. All right, so we're going to partition our whole interval into n sub-intervals. So we have n slices of our bread. So partition AB into n sub-intervals. With partition points, A equals x0, and then we have other partition points, x1, x2, all the way through xn, which will equal b. We're going to divide our object S into slices of width delta xi, which is the distance between the two places where we're slicing. So don't get too scared by all this. We are just walking through the theory of what this is, just to develop the formula that we're going to use, and then we're going to use a lot of examples to solidify this. So right now, just hang in there and try to follow your way through the theory, and know that the basic idea is slice the three-dimensional object, find the area of the face of the cross-section, and then we're going to do something adding these up and taking a limit. So, we're going to choose sample points xi star in each subinterval xi minus 1 to xi. So this is just saying choose any x value that you want in each little subinterval. It can be one of the endpoints, it can be the midpoint, it can be anything. It doesn't really matter because eventually we're going to take a limit and smush all those subintervals so that they're infinitely thin. So we're just choosing some representative point in here, and then we can approximate the ith slice as a cylinder with base area A of xi star and height delta xi. So again, what we were doing, we sliced this all up, and I told you to think of a piece of bread. So here's our piece of bread. We said A of x was the area of the face. And now we're saying we're going to estimate this piece of bread with a cylinder. And yes, we are. What we're going to do is picture this like this. It's a very thin cylinder. The height of the cylinder is going to be my delta xi, because remember, these cylinders are originally facing sideways like this. And then the base of the cylinder is the area of the piece of bread. So if this were a perfectly circular piece of bread, you would have the volume of this bread just by your standard volume of a cylinder formula. Now, this isn't going to be a perfect cylinder, but you can still find the volume of it using the area of the base times however thick the slice is. So we're estimating all of these slices as cylinders. And now we're going to add these cylinders up. So if we add the volumes of the slices, we have an approximation for the volume of our solid S. The volume is approximately equal to a sum from 1 to n of the area of that cross-sectional face times the height of that particular cylinder. Now, when we take more slices, we're going to have a more accurate volume. Equivalently, taking more slices means the slices get infinitely thin. So, as the thickness of the slices approaches 0, we're going to get the actual volume. And here is our definition. So for those of you whose eyes are glazed over from talking about the theory, time to wake up now. We're about to get the actual formula that we're going to use on these problems. All right, so we have the actual formula is the volume is equal to the limit as the maximum width of our slices goes to 0 of this sum. And that still looks pretty terrible. But remember, when you take a limit as the number of slices goes to infinity, or equivalently as the slices get infinitely skinny, this spits out a definite integral, just like we got in doing area. So the formula that we actually use in practice is after we take the limit and we get that the volume of our object is equal to the integral from sum a to b of a of x dx, where this a of x is the area of the cross-sectional face. So when we're trying to find our volume using this method, what we're going to do is kind of sketch what's going on and imagine slicing it. Slice it, open it up, and picture what that face looks like. Come up with a formula to represent that area of that face, and then all we have to do is integrate that area formula, and we'll get our volume. All right, so just to convince you that all of this is actually true, it's not just some made-up thing, we're going to start with an example where we prove a formula from geometry, but we're going to use this method to get the formula. So hopefully from geometry, you remember what the area of a sphere is. So we're going to show that the volume of a sphere with radius r is equal to 4/3 pi r cubed. Hopefully that formula looks familiar, because then this will help convince you that this is a valid way to find volume. We are going to find the volume of a sphere by drawing it out, slicing it, finding the area of a cross-sectional face, and integrating that area. So first, let's go ahead and just do a real rough sketch of a sphere. I'm going to center it at 0, 0, so I have a three-dimensional sphere here. Pretend it's three-dimensional. I'm pretty terrible at graphing in 3D, but I think you can imagine that this is a ball. So an equation of a sphere with radius r, and it's centered at 0, 0, we are going to have, well, the circle is going to be x squared plus y squared equals r squared. That gives us a circle. So let's take a second and take a look at a slice of this sphere. If I take a slice, I'm just going to slice it right here. Picture taking a ball and chopping the ball. What happens when you then open the ball up? What's that face going to look like? A cross-section face is going to look like a circle with radius y. How do I know that the circle has radius y? Well, because my circle, remember, is the cross-sectional face. The radius of this circle here is this distance from the x-axis to one side of my circle. Now this is a little hard to imagine because my circle is facing sideways here, so you can't really see it on this board. Remember, I'm slicing my sphere and opening it up. So my circle has a radius of y, and using this equation I can solve y is equal to the square root of r squared minus x squared. So, what is the area of this cross-sectional circle? My cross-sectional circle looks like this, and my area is equal to pi times the radius squared. The radius of my cross section is y, which is the square root of r squared minus x squared. So my area formula is just pi times r squared minus x squared, because when I square that square root, that part goes away. All right, so that is my area formula. Now, using that definition that we just came up with all of our theory, I know that my volume will be equal to the integral from an A to a B of the area of my cross-sectional slice. So I'm going to integrate the area of that slice. And now we just have to find what our A and our B were. Now, I just erased the sphere, but it looked like this. And since my sphere had radius r, my x values are ranging from negative r to positive r. And now let's go ahead and just calculate this integral. I'm going to pull the pi outside. You don't have to, but I found a lot of my students tend to like it better with the pi pulled out, so I try to do that for them. And now we just have to calculate this definite integral to get our volume. So I'm going to have that pi multiplied on the outside. Antiderivative of r squared, be careful. R is a constant. I'm integrating with respect to x. The antiderivative of r squared is not going to be r to the third over 3. It's going to be an r squared times an x, because r squared is just a constant. Now the antiderivative of x squared, I get an x to the third over 3. And I'm going to evaluate this at r and negative r. And now be very careful, we're going to have lots of negatives floating around and lots of r's. So just be careful simplifying. I'm going to have a pi. When I plug in positive r, I'm going to get r squared times r, which is r to the third. And I'm going to get an r to the third over 3. And then I'm going to subtract what I get when I plug in negative r. When I plug negative r in, I get a negative r to the third. And then I'm going to have a negative r cubed. So that makes it plus r cubed over 3. Be very careful with all those negatives. Now I'm going to distribute that negative and simplify. R to the third minus r to the third over 3 plus r to the third minus r to the third over 3. So I have my pi times, well, r to the third plus r to the third is 2r to the third. And then I'm subtracting 2/3 r to the third. All right, well, if I made a common denominator here, 2r to the third is the same thing as 6 over 3 r to the third. So the 6 over 3 minus the 2 over 3 is, surprise, 4 over 3. So I get pi times 4 over 3 r to the third, and that is the exact same thing as the formula that you were told way back in high school geometry, 4/3 pi r cubed. And there we go. That's where the formula for volume of a sphere actually comes from. You just were handed that formula back in the day, and now you know how to actually derive it. So hopefully this helped convince you that using integration to find volume actually works, because we use the method to derive a formula that we already knew. All right, let's do some more examples, because really the best way to get good at these volume examples is just to do a bunch of them and get used to the idea. So let's do a couple examples that are similar to what you might see on some homework or quizzes or exams in your Calc 2 class. Let's find the volume, V, of the solid obtained by rotating about the x-axis, the region under y equals the square root of x from 0 to 1. All right, let's get an idea of what's going on here. Let's sketch what we're talking about first. So the square root of 0 is 0, and the square root of 1 is 1. My square root function looks something like this. And we're only concerned with the part from 0 to 1. So it says take the whole region underneath this curve. So we're taking this shape here, and we're going to rotate it around the x-axis. So now we have to use our imagination a little bit. Picture taking this curve and everything under it and rotating it all the way around this x-axis, making a three-dimensional object. So this graph is lifting off my board, coming towards you, and then goes down and through my wall and back up to the other side, making this three-dimensional object. What does this object look like? Well, let's just do a really rough sketch of what this object would look like. It looks like our square root of x up on the top, and it looks like the other side is the same thing, and it's going to be some three-dimensional solid object. You can kind of picture this as like a bowl facing sideways, and it's completely filled up. It's filled in sideways bowl. All right, so now we need to find the volume of this sideways, solid, filled in bowl using our method of slicing. So what we have to do is picture slicing this object. So I'm going to just take the red marker and we'll picture chopping this object right here. It doesn't matter where you slice it because we just want to know what does this look like when I slice it, and then remember we're slicing and then opening it up. So if I slice this object here, opened it up and faced it towards you, what does that cross section look like? Well, it should look like a circle or a disc. So my cross section it's a disc or a circle. And what would be the radius? Well, the radius of this cross-sectional slice is this distance here from the middle to the top. And what is this distance given by? Well, my original equation, square root of x. So we have a disc with radius r equals the square root of x. So now we need to find the area of that cross-sectional slice. Well, the area of a disc, that's just the area of a circle, pi r squared. So I have pi times my radius squared. And my radius was that square root of x. This is my area function. If I simplify this, I get a of x is equal to pi times x, because that square root and the squared are going to undo each other. So this is what we get to integrate. My volume is equal to an integral of my area function with respect to x. And now all I'm missing is the bounds of integration. Since I'm integrating with respect to x, these are going to be x values. My smallest x value was 0, and my largest x value was 1. So that is what we need to do to find that volume. All right, so the hardest part of these problems is getting it set up. Now that it's set up, that's just a Calc 1 integral. We can do that. We know we're going to have our pi. Antiderivative of x is x squared over 2. I'm just going to pull the over 2 in front by the pi. Plug in a 1 and plug in a 0. When I plug in the 1, I'm going to get pi over 2. And when I plug in the 0, I'm going to get 0. So the the volume of that object, that sideways filled in bowl, is going to be pi over 2. Now I'm going to tell you right now, most of these volume problems are going to have a pi in the answer. And that's just because most of our areas of the cross-sectional faces are going to be like a circle or something involving circles. So that area is going to involve pi in some way. All right, so we just survived our first actual problem of finding the volume of some object that we created. Let's do another one. Our next one, we're actually going to integrate with respect to y, just to show you that we can do it that way too. So let's find the volume of the solid obtained by rotating the region bounded by y equals x to the third power, y equals 8, and x equals 0 about the y-axis. So let's just do a quick sketch of what this looks like. X to the third, but only on this right side here. This is 8 up here. I know my x to the third looks kind of like that. It also goes down on this side, mirroring that. But since I'm chopping it off at x equals 0 there, we're only considering this right-hand side of this curve. And we're chopping it at y equals 8. So we're talking about this solid region here. We're taking that solid region and it says rotate it about the y-axis. So it's rotating this way. So you can picture this object coming out of the board, going around the y-axis, through the wall, and what do we end up with? Well, when I rotate it around, it's going to be symmetrical on the other side, chopped off at the top, and it's a solid object here. Picture that like it's another bowl that's filled in, it's just this time it's right side up. So we have this bowl-like object, and we're going to be slicing it, this time perpendicular to the y-axis. Why do I know that? Because you always slice it perpendicular to the axis you're rotating around. So that previous example, we rotated around the x-axis and we sliced perpendicular to x. Now that we're rotating around the y-axis, I'm going to slice this perpendicular to y. So there's my red knife slicing this object. And what would I have when I sliced that and opened it and look at the face? Well, this is another bowl-like object, so we're going to have a disc for the face again. So our cross-section is a disc. It's a disc with radius. Is it going to be x or y? Well, my disc starts here in the middle and my radius goes to one side of this. That's moving in the x direction. So my radius is x. The only equation that we had before was that we had y equals x to the third, making that side of the curve. So this means x is equal to the cube root of y. So what is the area of this cross-sectional slice? Well, it's going to be a disc again, so that's a pi times our radius squared. And my radius is the cube root of y. So notice when we rotate it around the y, we're having everything in terms of y. When we rotated around x, we had everything in terms of x. That's for this particular method of slicing. So let's go ahead and simplify this area function, and then we can integrate it. This is the same thing as pi times y to the 2/3 power. Remember that the root gives you a fractional exponent, and the 2 is just like a regular exponent. So the 2 goes on the top, and the root goes on the bottom. So this is the area of a cross-sectional slice. And that means that my volume is equal to the integral of this area with respect to y. And all I'm missing is the bounds of integration. Now, I already erased what the picture looked like, but remember we had that bowl-like object. It started at 0 for my y values, and we chopped it off at y equals 8. So we integrate from 0 to 8. Now we have to find this antiderivative using our power rule. So I still have my pi. Now I'm adding 1 to my exponent, so I get y to the 5/3, and divide by 5/3. That's the same thing as multiplying by 3/5. Then we're going to plug in the 8 and plug in the 0. Now, when I plug the 0 into this guy, I'm going to get 0. So really, I just need to plug in that 8 to find the answer. And I'm going to get 3/5 times pi times 8 to the 5/3 power. Well, what is 8 to the 5/3? So you could type it into your calculator, but you can also do the cube root of 8, which is 2, and then 2 to the 5th, which is 32. So I get 3/5 pi times 32, which is the same thing as 96/5 pi. And that is my volume. And like I said in, I believe it was the last video, do not round your answers unless you are explicitly told to do so. It is okay to leave pi's in your answers. It makes it much more accurate. So only round if you're told to do so. Otherwise, leave your answers as exact answers so you can be as precise as possible. All right, so that particular volume problem was a little tricky just because we were integrating with respect to y instead of x, but it's still the exact same concept. Slice it perpendicular to the axis you're rotating around, find the area of that cross-sectional face, integrate that area. All right, so I have 2 examples left for us. And you might be wondering, well, at the very beginning, the title of this video said that we were doing slicing with discs and washers. We've had all sorts of discs, but what in the world am I talking about with a washer? Well, that's what this next example is for. We're going to have a washer this time. So let's figure this out. So find the volume of the solid obtained by rotating the region enclosed by y equals x, y equals x squared, about the x-axis. So y equals x, we know, is a diagonal line, and y equals x squared is our parabola. So when I graph these guys, the region that we're rotating is this sort of banana-shaped object, and we're rotating that about the x-axis. So what kind of solid object do I get when I rotate this guy around the x-axis? Well, it's going to be a sort of banana-shaped object this way. And then you just have to imagine that 3-dimensionally. It's kind of hard to draw it, and it's kind of hard to imagine it. But what this is kind of a sideways bowl, except we actually have space inside the bowl this time where we can put stuff into it. So what would happen if I were to slice this object? Well, if I slice this object and open it up, what does the cross-sectional face look like? Remember, this is going all the way around, so you might think it's a circle. But we have all of this empty space in the middle. So what the object looks like is something like that. There's a hole in the middle. Other than that, it looks like a circle. This is why it's called a washer, because it looks like a washer when we're talking about hardware stuff. So here is a washer. And how do we find the area of this washer? We have all of that stuff solid and a hole in the middle. Well, if I didn't have a hole, the area of this would just be a pi times a radius squared. And the area of the hole is also pi times a radius squared. So in order to find the area of this washer face, I need to know what this outside radius is, and also what the inside radius is. And the area is going to be the area of the outside circle minus the area of the inside circle. So my area function is going to be pi times the outer radius squared minus pi times the inner radius squared. So now we just have to figure out what the outer radius and the inner radius are looking at our graph. Well, the radius, remember, always goes from the center of the object. So my outer radius is from the center of the object to the very outside of the object. Is that the straight line or the parabola? It's a straight line. So my outer radius is given by the equation of the straight line, y equals x. My inner radius is the distance from the very center of my object until I hit the very first part of my object, so that little green distance. Is that inner radius matching the graph of the straight line or the parabola? This one's the parabola. My inner radius comes from y equals x squared. So my area function is pi x squared minus pi x to the fourth. Or I can factor out the pi if I want to. Pi times x squared minus x to the fourth. That is the function we are going to integrate to find the volume of that object. So I know my volume is going to be equal to a definite integral from sum a to sum b of pi times x squared minus x to the fourth with respect to x. So now I just have to find the bounds of integration. And how do we do that? Well, those are the x values where the two graphs intersect each other. So let's find our bounds real quick. My two graphs intersect each other when their equations are equal. This is the same thing as 0 equals x squared minus x, or 0 equals x times x minus 1. This means my bounds of integration are 0 and 1. So I have my volume is pi times x squared minus x to the fourth dx, and I'm integrating from 0 to 1. All right, so now we're ready to find the antiderivative so we can find the object's volume. I know the pi is going to come out. Antiderivative of x squared is 1/3 x to the third. Antiderivative of x to the fourth, 1/5 x to the fifth. And then I just have to plug in a 1 and a 0. When I plug in the 0, I'm going to get 0. So what happens when I just plug in that 1? Plugging in the 1 gives me a pi times a 1/3 minus a 1/5. If I change that into 15ths, I get pi times 5/15 minus 3/15. So I get that my volume is 2/15 times pi. And that gets me the volume of that kind of weird bowl-like object that had a curved inside. All right. Let's do one last example, volumes with slicing, and it's going to be the most complicated example so far. Find the volume of the region enclosed by y equals x and y equals x squared, rotated about the line y equals 2. So really, this object that we're rotating, it's the same object we just did, that sort of banana shape. We had our straight line and our parabola, and we know it went from 0 to 1. We already know what our bounds are going to be. But we're rotating about a different line this time. We're rotating about the line y equals 2, which is way up here. So I'm going to take this object, lift it up, rotate it all the way around that line, and see what happens. So if I rotate this all the way around that line, what is going to happen to this object? Well, what we're going to have is going to be kind of banana shaped again, but looking like this. There's the banana shape. And then just picture this banana shape going all the way around to this one. And what we end up with, I really had a hard time drawing these, but hopefully you guys have a good imagination here. Picture taking this, rotating it all the way around, and what you end up with is a very wide bowl on its side, and somebody punched out the bottom of the bowl. So we just have the sides of the bowl, and it's a hole at the bottom. So in order to find this volume, we're going to take a cross-sectional slice. There's the slice, and remember that these pieces are connected all the way around. So what is the cross section going to look like? Well, we have this gigantic hole in the middle. We know it's going to be a washer. And we need to find our outer radius and our inner radius. So now is where it gets a little bit tricky, finding the radius for both of these. So remember, the radius is going to be your distance from the center of the object. We're going to start with the outer radius. That's the distance from the center of the object to the outside of our solid shape. So what is the length of that little green line I just drew there? Well, first notice that it does match with our curve x squared. And you know what? I apologize for that. That is an outer radius, but I'm going to use the outer radius this way, going to the downward direction, just because that's our original graph. It might make it a little easier for us. So, looking at this outer radius in green, what is this distance? You can tell that it involves the parabola curve, so it's going to involve the x squared. But is that distance x squared? No, it's not. The distance from the x-axis all the way to the center of our object is 2. And I'm subtracting this little gap here between the x-axis and my curve. So my outer radius is that whole distance 2 minus my x squared curve. Now what's my inner radius going to be? Well, the inner radius is the distance from the center of the object until I reach the inside. Well, that's going to involve my straight line. The distance from the x-axis all the way to the center of the object is 2, and I have to subtract the distance from the x-axis to my straight line, 2 minus x. So I have the outer radius is 2 minus x squared, inner radius is 2 minus x. So what is the area going to be? My area function is pi times my outer radius squared minus pi times my inner radius squared. That is the function that we are going to integrate. And if you distribute everything, this simplifies to pi times x to the 4th minus 5x squared plus 4x. Go ahead and check that if you want to check all your algebra skills. This is the function that we are going to integrate to find the volume of that strange bowl that does not have a bottom. My volume is the integral of this area. With respect to x. And what are my bounds of integration? Well, my smallest x value was 0 and my largest x value was 1. We found those in the previous problem where those two curves intersected each other. All right, so now let's find this antiderivative so we can find the volume of that object. So we have a pi times 1/5 x to the 5th minus 5/3 x to the 3rd and plus a 2x squared. And we have to plug in our 1 and plug in our 0. Plugging in the 0 will result in 0. Plugging in that 1 gives me pi times 1/5 minus 5/3 plus 2. And then we just have to simplify this to get the answer. And if I turn all of that into 15ths, we would have 3/15 minus 25/15 plus 30/15. And this is equal to 8/15 times pi for that volume. All right, so you have quite a few examples now on how to find the volume. Remember that in order to find the volume of these objects, you're going to slice it up like a loaf of bread and find the area of that cross-sectional face. You always slice it perpendicular to the axis that you're rotating around. Using this method, when you rotate around an axis that goes in the same direction as x, you're going to integrate with respect to x. If instead you're rotating around a vertical axis that goes like y, you're going to integrate with respect to y. Always take a slice perpendicular to your axis of rotation, find the area, and integrate the area. Most of the time, the area of the faces are going to be circles or washers, but they really can be anything. So you better watch out because they might have some really strange areas to look at. Make sure you're finding the area of the face that you have. If you have any questions, feel free to drop them below. If you're a current student, you can also ask in office hours or through email. And I'll see you guys next time to learn another method for finding volume called the method of cylindrical shells. See you next time.